For our video lecture, we're picking up where we left off on March 29th. We're going to talk about the Henry Bent guidelines. Everything that we've discussed so far assumes that all of the ligands that are attached to the central atom are equivalent. And so we start out the same way we did in that case. Central atoms are going to be classified to start out with as sp3 or sp2 or sp based on the number of charge clouds that are surrounding it. But if the ligands are not all the same as one another, and we're including lone pairs as ligands here, then we need to account for that. There's going to be a bond angle change, an S and P character change to the bonding orbitals, to the hybridized orbitals, that occurs because of that. So ligands are going to be classified by how electronegative they are. And we know electronegativity from general chemistry. Fluorine is the most electronegative atom on the table, and then oxygen and nitrogen and chlorine and so on. And so the first atom in the ligand is going to be the primary determiner of that case. But again, like I said, we're comparing those to lone pairs as well. So a lone pair is going to be thought of as a less electronegative ligand or a more electropositive ligand than any other atomic or functional group ligand. And the reason why we're going to do that is because it's known that orbitals that are going to bond to more electropositive ligands or form the orbitals of those electropositive ligands tend to concentrate a little bit more S character than we would expect based on their starting hybridization of sp3, sp2, or sp. And so more P character then is going to concentrate toward the more electronegative ligands, and from that we see different bond angles. A perfect example of this is the water molecule. We know that sp3 carbon, when we look at a molecule like methane, has a bond angle of about 109 degrees, but water has a bond angle of about 104.5 degrees. This is because lone pairs are more electropositive than hydrogen atoms, or hydrogen atoms we can think of as being more electronegative. So more S character gathers toward the lone pairs, and that widens their bond angle and narrows the bond angle going toward the hydrogens. So in order to describe water properly, we're going to need two equivalent bonding orbitals that are normalized and that are at that angle, 104.5 degrees, to one another. To make the math a little bit easier, we're going to operate in the YZ plane for those two orbitals, and so we can take a look at what that would look like. We'll think of the oxygen as being at the origin, and that means one of the hydrogens is positive Z from the origin and negative Y, and the other is positive Z and positive Y. And so we're going to use those principles to help develop at least the signs of the coefficients that we see in the orbitals that we're going to develop. To develop the numerical coefficients, we'll start with a similar idea that we started to when we were doing the more symmetric case, but this time we're going to use some trigonometry to help us out. So looking again at this picture, we can see that this particular hydrogen, which we're going to say is bonded to hybridized orbital A, so we'll call this one hybridized orbital A, is positive Z, so we have positive number for Z, and positive Y as well. But the question is, how far positive in each case? So we're going to use trigonometry to figure that out. If we consider that cosine is adjacent over hypotenuse, we can tell from trigonometry that cosine of theta will give us the coefficient that's related to the amount of Z that's there, because that adjacent is going to be this length here. If the angle is 0 degrees, we'd be right up the Z-axis, and cosine would be 1. But we're further out. If the angle were 90 degrees, we'd have no Z component. Cosine of 90 degrees is 0. And by the same token, sine is opposite over hypotenuse, so sine is going to tell us the Y component. And then the question that comes up beyond that is, how do we tell how much of the 2S component is involved? In other words, what is alpha? And the way that we can go about dealing with that is with one of our main principles. We used normalization last time. We're going to use orthogonality this time. These two orbitals have to be orthogonal to one another, which means if we multiply them by one another and integrate over all space, we have to get 0. So you can pause to look at the math here if you want to. I'll explain it a little bit, but take some time and look at it more closely if you'd like to. What I've done here is I've drawn out what we have of the two orbitals. So here's orbital A, here's orbital B. And so what we need to do is multiply these. We call it foiling, but there's more terms than that. But still, we need to multiply these out and see what we would get. So we'd get cosine times cosine of PZ times PZ. So that's this first term. We'd get the sine squared 2PZ squared. So we have that right there. And then we would get alpha squared times the 2s component squared, and so we have this right here. And notice I've left all the other terms out. Alpha times sine, cosine times alpha, and so on and so on. And the question is, why would I do that? Well, we know that if the 2pz orbital is multiplied by the 2px orbital, as it would be in the sine cosine term, that integral has to be 0, because those orbitals, the px and the pz, the 2s and the 2px, and so on, are orthogonal to one another. So we would generate 9 terms here, but only 3 of them survive, only the ones that have the same orbital under the integration. The other neat thing is that those orbitals not only are orthogonal to each other, but they are normalized in and of themselves. So this integral right here, the pz integral, is 1. So that term becomes just cosine squared. This term becomes just sine squared. This term becomes just alpha squared. Now to simplify the math even a little bit further, I'm going to use the trig identity that cosine squared minus sine squared is the same as cosine of 2 times the angle that's described. So that brings us down to, and we can drop the n squared if we're going to set this equal to 0 for normalization, because the n squared divides out. And so we're left with just cosine of 2 theta plus alpha squared equals 0, or cosine of 2 theta equals negative alpha squared. So that tells us that alpha has to be the square root of negative 2 times the cosine of theta. So we can rewrite this set of orbitals up here, placing that number for alpha. So we'll go ahead and do that on the next slide here. And then we can remember that theta is 52.25 degrees, and so we can substitute that number in and take the cosine of it, the sine of it, the cosine of it, and calculate all these numbers. So we have a set of orthogonal orbitals whose angles to one another represent the angles involved in the water molecule that are known experimentally. All that's left for us to do at this point is to normalize the pair of orbitals. They'll both normalize in the same fashion, and I'll show you that on the next slide by taking orbital A and squaring it and setting the square of it equal to, setting the integral of the square of it equal to 1. So here we have our n squared that we can factor out after we've squared the orbital under the integral. When we FOIL this, we end up with the same situation we did earlier, and that is only 3 terms survive. Only the z times z, the y times y, and the s times s terms survive, because all of the other ones are 0 because of orthogonality. So we end up with 0.61 squared times the integral of the z squared orbital times plus 0.79 squared times the integral of the 2py squared orbital, and then so on for the s orbital. But again, these are normalized orbitals, so their integrals are 1. So 1 equals n squared times the sum of those squares. They work out to be 1.25. We can put that all in our calculator. So 1 equals 1.25 times n squared. That means that n squared is 4/5, and n is the square root of 4/5. That's 0.89. So if we go ahead and multiply both of those orbitals we calculated through by 0.89, that drops the coefficients from 0.61, 0.79, and 0.5 to 0.55, 0.71, and 0.45. And what we end up with is two orthogonal orbitals that are at the correct bond angle and are completely normalized. And we've got the orbitals for the bonding orbitals for water. Now, if we wanted to go a little bit further and get the orbitals for the lone pair, two lone pairs that are also on that oxygen atom, we could do that by writing a psi C and a psi D right below this, and using the numbers that we've already got here and the ideas of normalization and orthogonality to fill in what the other components of the X, Y, and Z and 2s orbitals would have to be for those. And I'll probably leave that for you to do on a homework assignment. So I suggest that you try that out, and we can talk about that in the review session next Friday, if that might be helpful for you in preparing for the test that will happen the following Monday.